Is this actually okay? It is going live. All right. Planck and Einstein. So, black body radiation. You heat something up, it glows. You have probably seen this at home with your stove. It'll start out glowing red, and then it'll go bright red. You can actually see it in the picture here. It goes from red to bright red to orangey to yellowy to golden to just white hot. Okay. This is known as black body radiation. Because they sort of, in order to come up with their model, they said, okay, you have a hypothetical thing that's perfectly black. It absorbs all light, and it emits all light perfectly equally. So, black body radiation. Now, this glow, when you heat things up, is predictable. The problem is they couldn't predict it. Okay, this is, these curves down here in the lower right are what we actually see. We have the red curve for a thing at fairly low temperature. Then we have a higher temperature, 4,000 Kelvin, higher temperature still, 5,000 Kelvin. Nice and predictable. And then over here, this black line is classical theory. You'll notice that it starts out doing okay-ish, and then it just goes completely off the rails. This was called the ultraviolet catastrophe, because this line goes up, it never ever comes back down. Over here we have ultraviolet, where things are completely nuts and wrong. So ultraviolet catastrophe, because 19th century physicists were nothing if not totally drama. And so when they saw that their theory just didn't do the thing, their response is, oh my god, I just can't. And they just sort of left it at that. They assumed that eventually someone would be able to solve the problem, and they sort of ignored it. So along comes Max Planck. I can, even. So the thing is, over here on the right we have math. This is formal logic. Here at the top, these first four lines, these are your assumptions. Okay. Down here on the bottom, you have math, when you're doing stuff using those assumptions. So all math follows a formal logic structure. It doesn't necessarily look exactly like this, but it does much the same thing. You have your assumptions, you proceed from there, you do math, math, math until you get to a conclusion. If your assumptions are right and your math is right, your conclusion will be good. If your conclusion is wrong, then either your argument is unsound or invalid. Meaning either your assumptions are wrong or your math is wrong or both. In this case, Max Planck looked, he said, okay, your result is crap. Your result is this line right here that goes up to infinity and never comes back down. Your result is crap. Your math is good. Therefore, your assumptions must be bad. So he started playing around with the assumptions. And this is basically theoretical physics, where you say, okay, what if the universe is like this? And then you math, 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 and hopefully you come up with some sort of result that researchers can look at. Theoretical physics is basically playing around with pocket universes. So eventually, Planck came up with an answer that worked. And he did that by changing the assumptions about the way light behaves. So, in classical physics, light is a wave like an ocean wave. And Planck said, okay, it's a wave, we see that, but it's not like an ocean wave. It is different. In classical physics, light is infinitely divisible. Planck said, no. Light comes in discrete packets of energy, individual particles of light that he called photons. That's from Latin photos, meaning light. In classical physics, the energy of a wave is defined in the amplitude. Remember, amplitude is the height of the wave. For an ocean wave, that's literally the height, how far the water is displaced from level. For light, the amplitude is the brightness of the light. So the brighter the light, the more the amplitude there is, the more energy there is in that wave. Planck said, no, amplitude is not the energy of the wave. It is the number of photons. How many photons there are would give you more light, because more photons means brighter light. For classical physics, wavelength and frequency are just characteristics of the wave. Planck said, no, they are more than that. They are fundamentally tied to the behavior of light. And when he did that, this is the result. The squiggly looking red line here is the actual observation of a 5,780 Kelvin object. That's very hot, by the way. And then the orange smooth curve is Planck's prediction. In other words, he absolutely nailed it. He got it exactly right. So obviously, the physicists of the early 20th century said, wow, you are a genius. We love the work you are doing. We are going to celebrate you. Or not so much. Physicists at the time said, you just got lucky. Shut up and go away. Planck was a little bit bitter about this. He said, eine neue wissenschaftliche Wahrheit pflegt sich nicht in der Weise durchzusetzen, dass ihre Gegner überzeugt werden und sich als belehrt erklären, sondern vielmehr dadurch, dass ihre Gegner allmählich ausstößen und dass die heranwachsende Generation von vornherein mit der Wahrheit vertraut gemacht ist. Wow, you know? Okay. Here's the translation. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it. Okay, first off, one hardcore. Germany has always been metal as hell. Second, pun, because he was dealing with light and see the light. Okay, so are photons a thing? Physicists can be incredibly esoteric. When they're doing their theoretical modeling, sometimes they say that the thing they're working with is definitely real. Other times they say, no, it's a convenient tool. It lets us make predictions, but it's not necessarily real. It might just be a useful fiction. Sometimes they argue about this. Sometimes they say both at the same time. Planck was convinced that photons were real, that they are, in fact, the way that light works. Put a pin in that. Photoelectric effect. So the photoelectric effect, exactly what it says on the tin. You shine a piece of light, photo, on a piece of metal, electrons will come flying off, electric. This, by the way, is kind of the basis for photocopiers. You shine light on a piece of metal, electrons come off, and that is how the detector knows that the thing you're reflecting the light off of, paper, is light or dark. So, classical physics said that light means greater amplitude, has greater energy. Therefore, if you shine brighter light or greater amplitude light on the piece of metal, you're going to get higher energy electrons coming off of the metal. That is to say, they'll have higher kinetic energy. They'll be moving faster. They'll have more impact when they hit things. And frequency will have nothing to do with it. Now, when you actually study this, greater amplitude does not affect the energy of the electrons. Instead, you get more electrons with brighter light. And instead, higher frequency is what gives you higher energy electrons. Or to put it another way, classical physics is just plain wrong when it comes to the behavior of light. So here comes Einstein in Planck. He said in German with a Swiss accent, which I don't know how to do, so I'll just continue with my father's friend Otto. I dig it. Let's scroll, son. He noticed in Planck's math this guy here, the letter H. I didn't show you Planck's formula because it's really complicated, but when you're doing theoretical physics, when you're working with calculus, basically, very often you get constants showing up. They're necessary to balance out the math, more or less. So when Planck did his work, he came up with this letter H. And when he actually plugged it in and balanced it out with real-world stuff, it had this value. 6.626 times 10 to the negative 34th joule seconds. The H, by the way, is now known as Planck's constant. And yeah, so when Einstein saw this unit, saw this constant, and he saw its units, he got clever. He said, all right, energy has the unit of the joule. Frequency has the unit of the hertz, or 1 per second. So, E equals h nu. The energy of a photon of light is equal to Planck's constant multiplied by the frequency of that photon. Put it another way, a lower frequency means lower energy, higher frequency means higher energy. So, the way he worked this out, he said that the electron is bound to the metal. It has to be, otherwise electrons would just come flying off without any prompting by light. So they have to be bound to the metal. And they're bound to the metal with a certain amount of energy. He called the amount of energy binding the electron to the metal the work function. And they symbolized that with the Greek letter phi. He called it the work function because it's the amount of work that the light has to do to pull the electron off. So, he said the incoming photon has a certain amount of energy, E equals h nu. The electron is going to be knocked off of the metal if the light has enough energy, if the energy of the photon, h nu, is at least equal to phi, the work function. You rearrange that, you get nu sub 0. That's the minimum frequency of the light is equal to phi divided by h, the work function of the metal divided by Planck's constant. And he said that, to put it another way, the energy of the electrons is going to be K, or the kinetic energy of the electrons, is going to be equal to h nu, the energy of the incoming photon, minus the work function. So the photon has a certain amount of energy, it does a certain amount of work, phi, and the energy left over is going to be the energy of the electron. So that is how Einstein explained the photoelectric effect. And this works. It worked perfectly well. It explained the photoelectric effect, and it confirmed that Planck was right about black-body radiation. He was right about photons. Okay? So the amplitude of light looks like energy. I mean, 19th century physicists were not idiots. Okay? It looks like energy because it has more individual photons. Each photon is a packet of energy, so you have more total energy in the light. So greater amplitude, more photons. And in terms of the photoelectric effect, more photons is what gives you more electrons. Individual photons have energy determined by frequency. Higher frequency means that each photon has more energy, which is why higher frequency gives you higher energy electrons. It also explains the fact that below a certain frequency, there are just no electrons coming off the metal at all. And this is what won Einstein the Nobel Prize. It wasn't his work on relativity, it was his work on the photoelectric effect. It's because he confirmed Planck's quantum mechanics. Okay. So, before we get into that, let's just say quantum mechanics is the branch of physics where you deal with individual bits of tiny bits of energy, tiny bits of matter. It is modern physics. Classical physics deals with balls rolling down ramps, planets moving through space. Quantum mechanics deals with electrons and photons. Relativity deals with gravity and so on. Things moving through very large swaths of space. Eventually, they will find a way to connect quantum mechanics and relativity, and when they do that, there will be a Nobel Prize in it for someone. All right. So these are the sort of math problems that they can throw at you when we are talking about black-body radiation and the photoelectric effect. That is to say, they will not be throwing any math at you from black-body radiation. Planck's formula is just way too complicated, and it's a real pain in the keister. They will probably throw some sort of problems at you related to the photoelectric effect. So, these are the mathematical formulas and constants related to that. E equals h nu tells us the energy of light as related to frequency. So the energy of a photon will have a certain amount of energy dependent on the frequency of the photon. The K equals h nu minus phi is the energy of an electron, K, kicked off by light, h nu, from a piece of metal with a work function, phi. And then, of course, speed of light, c equals lambda nu. We need that because energy and so on is based on frequency, but we often talk about light in terms of wavelength. So finally, the constants. Planck's constant h, 6.626 times 10 to the negative 34th joule seconds. And the speed of light is 2.998 times 10 to the 8th meters per second. So problem 1. What is the minimum frequency of light needed to remove electrons from metal with a work function phi is equal to 3.482 times 10 to the negative 21st joules? All right, let's grab blue again. And let's go ahead, turn on that. Oops, there we go. All right. Let's move the camera a bit. All right. So, minimum frequency of light needed to remove electrons from metal. All right, minimum frequency means we're looking at h nu is equal to phi. Okay. So that gives us nu 0. Okay. That means the energy of the photon is exactly equal to the work function. That is how you get the minimum frequency. So nu 0 is equal to phi over Planck's constant. So the work function in the problem was 3.482 times 10 to the negative 21st joules. And Planck's constant, 6.626 times 10 to the negative 34th joule seconds. So joules will cancel out, leaving us with units of 1 over seconds. So we go ahead, we plug this into our handy dandy, not very good calculator. 3.482 divided by 6.626 gives us 0.5255 times 10 to the 13th hertz, or 5.255 times 10 to the 12th hertz. Okay, did I ask anything else in that question? I often do. Nope, that's just the minimum frequency. Nu 0 is equal to 5.255 times 10 to the 12th hertz. Okay, second problem here. How much energy will an electron have if an electron could have energy? If metal with a work function 2.872 times 10 to the negative 20th joules is hit by light with a frequency of 3.283 times 10 to the 15th hertz. Okay. In this case, we're dealing more straightforwardly with the second equation here. Energy of the electron is equal to h nu minus phi. So, K, technically max, is greater than or equal to h nu minus phi. So, greater than or equal to 6.626 times 10 to the negative 34th joule seconds times 3.283 times 10 to the 15th hertz minus 2.872 times 10 to the negative 20 joules. Okay. Seconds times hertz will cancel out, so that first number will just leave us with joules. So let's go ahead and pull out the calculator. 6.626 multiplied by 3.283, negative 34 and 15, that's going to be negative 19. So that is 175 times 10 to the negative 18th joules minus 2.872 times 10 to the negative 20th joules. So there is way more energy than you need. In fact, it's about 100 times more energy than is necessary to pull that electron off of there. 10 to the negative 18th is 100 times more than 10 to the negative 20th. So what we could do to make it easier, this is 217.5 times 10 to the negative 20th joules minus 2.872 times 10 to the negative 20th joules. So it is, let's see, 8, 2, 6, 4, 1, 2 times 10 to the negative 20th joules, or 2.146 times 10 to the negative 18th joules. Okay. So that is the energy of our electron. Not a huge difference. Okay, so that's just the answer right there. That's the energy of the electron getting kicked off of the metal by light with a frequency of 3.283 times 10 to the 15th hertz. So the first problem there, what is the minimum frequency? That means that the energy of the light is exactly equal to the work function. In this case, it's asking about the energy of the electron, so K is equal to h nu minus phi. Okay, those are the two problems there. And then, moving in a slightly different direction, this next problem, what is the energy of a photon of light with a frequency with a wavelength of 450 nanometers? Okay. So we have to do two things here. First, we're going to have to convert from wavelength to frequency, and then we can plug frequency into E equals h nu. Or we can do sort of both at the same time. Okay. So the energy of our photon is h nu. Then the relationship between wavelength and frequency is c equals lambda nu. So we rearrange that. Nu equals c over lambda. We plug that in over there. E equals hc over lambda. So we can do it all at once rather than doing two separate problems. So it's equal to 6.626 times 10 to the negative 34th joule seconds multiplied by 2.998 times 10 to the 8th meters. Running out of room. Nope, I'm not even showing. I have not had that on this whole time. I am so sorry. So C equals lambda nu, meaning you rearrange that, nu equals C over lambda, and then we can plug C over lambda in for nu up here, so E equals hc over lambda. I'm sorry about that. Now we start plugging in our numbers. H is 6.626 times 10 to the negative 34th joule seconds. C is 2.998 times 10 to the 8th meters, and then our wavelength is 450 nanometers. All right, so our numbers all need to line up or it doesn't work. So times 10 to the negative 9th meters. Okay, so now meters will cancel out. Oops, sorry, that's meters per second. And then seconds will cancel out, leaving us just with joules. So our energy, once we start plugging in our numbers, what will that be? 6.626 times 2.998 divided by 450. All right. So 0.0441 times 10 to the negative 26, negative 17. Joules, move it over twice, equals 4.41 times 10 to the negative 19th joules. When you're talking about the visible frequency, light typically is going to be 10 to the negative 19th, 10 to the 20th, 10 to the 21st. Actually, it's just going to be 10 to the negative 19th, 10 to the 20th. It's not going to change very much from there. Visible light only occupies a very, very, very narrow portion of the overall spectrum. 400 to 700 nanometers is not a huge difference. Okay. And the final problem here, what is the wavelength of a photon of light with energy 7.128 times 10 to the negative 18th joules? No questions from the viewers. All right. So we bring this back up. So energy of a wavelength of light. So energy is equal to hc over lambda. We can rearrange that a little bit. lambda is equal to hc over E. Remember, being able to manipulate symbols like this will save you a lot of time so that you can sort of plug it all into a single thing if you have a decent calculator. If not, then you'll have to sort of do this all stepwise. All right, so separate problems. So lambda is equal to 6.626 times 10 to the negative 34th joule seconds. 2.998 times 10 to the 8th meters per second. Energy was 7.128 times 10 to the negative 18th joules. So seconds will cancel out there, joules will cancel out there, leaving us just with meters. Excellent. Plugging all of this into our calculator, 6.626 multiplied by 2.998 divided by 7.128. 2.787 times 10 to the what meters? Negative 34, negative 26. Yep. 26 minus 18 is going to be negative 8 meters. Or, put it another way, 27.87 nanometers. So this is not in the visible spectrum. This is way far off into ultraviolet. This is a lot shorter than the 400 nanometers of visible light. Okay, those are examples of different kinds of problems that they might throw at you from these particular sets of experiments. They could also ask you a little bit more, who's and what's it. They could ask you a bit about the black body radiation, but really what that amounts to is, spectrum of light, and Planck used it to develop the idea of photons. And then from that, he got the Planck constant, which Einstein used to explain the photoelectric effect. Photoelectric effect, they'll definitely ask you some math problems from that. And he confirmed quantum mechanics. He confirmed the existence of the photon. So those are the things you're going to need to remember from this. E equals h nu, k equals h nu minus phi, c equals lambda nu. You don't have to memorize these two constants. They will very likely give you those on the test. The one I feel they probably won't give you on the test is Avogadro's number from chapter 1. So be aware of that. Okay, so with that, my voice is starting to give out. That's 3 lectures today. So I'm going to go ahead and call it on 2.9, and I'll call it for the night. I will probably be able to wrap up chapter 2 tomorrow. I will also do a lab lecture. If not tomorrow, then Friday. Okay, I will see you.